The air inside the converter aisle did not smell like air. It smelled like the interior of the earth, sulfurous, metallic, thick with a heat that pressed against the skin like a living thing. The temperature at floor level held steady near 120 degrees Fahrenheit. Above the converter vessels, where the blister copper boiled at 2,100 degrees, the air shimmered and warped, distorting the faces of the men who worked within arm's reach of the molten surface. Those men wore no respirators. There were none issued. The sulfur dioxide rising from the converters registered, on the days when anyone thought to measure it, at concentrations 4 times beyond what a human lung could survive with repeated exposure. On most days, no one measured at all. This was 1906. This was Butte, Montana, or it was Garfield, Utah, or it was Anaconda itself, the city that the company built and named after the animal that squeezes the life from its prey. In all of these places, the same machine operated. The same men fed it. The same invisible gas descended into the same lungs and laid the same quiet damage into the same tissue, year after year, until the coughing began, until the weight in the chest became permanent, until a man who had worked the converters for a decade discovered that his breath no longer reached the bottom of his lungs and never would again. And yet, from that poison, from those converters, from the 600,000 tons of refined copper that poured out of those facilities between 1882 and 1920, came the wire. Every mile of it. The wire that crossed the continent. The wire that carried Niagara's power into American homes for the first time. The wire that made the grid possible. The largest, most ambitious electrical infrastructure the world had ever attempted. The machine gave civilization light. It took the light from the men who fed it. Every civilization makes a bargain it does not fully disclose. The bargain of the electrical age was copper, not the idea of copper, not the abstraction of it in ledgers and commodity reports, but the physical, extracted, smelted, poison-adjacent reality of it. Copper wire does not appear from engineering drawings. It emerges from or bodies blasted out of mountain rock, hauled through tunnels by men and mules, roasted at temperatures that vaporize sulfur compounds directly into enclosed air, cast through converters that operate continuously, day and night, without pause, for decades. The men who ran those converters made the modern world possible. Their names do not appear on the monuments to electrification. Their lungs do not appear in the technical histories. What appears is the grid. Luminous, celebrated, and absolute. That absence is not accidental. It was, in every meaningful sense, the policy. In 1880, the United States consumed virtually no electricity. Not because the technology did not exist. Edison's Pearl Street station in Lower Manhattan would open in 1882, feeding 59 customers from a single generating node, but because the infrastructure to move electrical power across distance had not yet been solved. A generator could light a building. It could not light a city. It could not light a state. The problem was not generation. The problem was transmission, and transmission was, at its core, a materials problem. Copper's electrical conductivity is surpassed among common metals only by silver. Silver could not be drawn into wire at industrial scale. Copper could. But the grade of copper required for long-distance transmission wire, 99.9% pure, free of oxygen inclusions, free of sulfur contamination, was beyond what most existing smelting operations could reliably produce. The electrification of America was therefore waiting, quite literally, for a machine that could refine copper ore at industrial volume and metallurgical precision simultaneously. That machine did not yet exist in 1880. By 1884, the Anaconda Copper Mining Company had begun building it. By 1892, it was operational at a scale that no industrial facility in the world had previously attempted. It sat in the mountains of Montana, and it ran on the labor of men who had no other options and were given no information about what the air around it was doing to their bodies. Marcus Daly did not build Anaconda out of vision. He built it out of necessity, which is a more reliable foundation. He had acquired the Anaconda mine in 1881 for silver. What his crews found at depth was not silver. It was one of the largest copper ore bodies ever identified on the North American continent. Low grade by the standards of the day, averaging less than 5% copper per ton of rock, but vast beyond any previous calculation. To make low-grade or profitable, you needed scale. To achieve scale, you needed infrastructure that did not yet exist. Daly built it. The smelter complex at Anaconda, Montana, was constructed between 1884 and 1902 in successive expansions that each dwarfed the last. By 1902, the facility covered 80 acres of operational floor space. Its primary smokestack, the Washoe Stack, completed in 1918, stood 585 feet tall, the tallest masonry structure in the world at the time of its completion, built not as a monument, but as a functional necessity, to push the sulfur dioxide output of 80 converters high enough above the valley floor that it would not immediately kill the surrounding livestock. The livestock, not the men inside. The distinction was economic. Cattle were property with assessed value. Workers were replaceable at $2.50 per shift. The converter itself was not a complicated machine. That was precisely what made it so dangerous. A Bessemer copper converter is a horizontal cylindrical vessel, typically 12 feet in diameter and 16 feet in length, lined with silica brick and mounted on trunnions that allow it to rotate on its axis. Molten copper matte, a mixture of copper and iron sulfides drawn from the furnace at approximately 2,000 degrees Fahrenheit, is poured into the vessel through an opening at the top. A row of tuyères, small steel pipes spaced along the lower cylinder wall, then injects compressed air directly into the molten charge at a rate of several thousand cubic feet per minute. The air oxidizes the iron sulfide first, then the copper sulfide. The iron oxide is absorbed into a slag layer and skimmed. The sulfur, with nowhere to go, exits through the open mouth of the converter as sulfur dioxide gas. There was no capture system. There was no scrubbing mechanism. There was no exhaust hood of meaningful design installed in most facilities before 1920. The gas rose from the converter mouth in visible blue-white clouds and dispersed across the converter aisle at the precise height where a standing man's face was positioned. The machine was not designed to kill. It simply had no design feature that prevented it from doing so. Sulfur dioxide does not kill quickly. That was the problem, or rather, that was the convenience. Acute exposure above 100 parts per million produces immediate incapacitation, burning eyes, constricted airways, fluid accumulation in the lungs. Men pulled unconscious from converter aisles during peak blows were documented in company medical records as early as 1895. The records classified these incidents as fainting. The gas concentration was not recorded. Chronic exposure at lower levels, between 5 and 20 parts per million, the range most converter workers inhabited across full shifts, produces damage that accumulates invisibly over years. Bronchial inflammation, scarring of the lower airways, progressive reduction in lung capacity that presents, to the uninformed observer, as ordinary aging, ordinary fatigue, ordinary susceptibility to the pneumonias and tuberculosis that swept through mining communities with statistical regularity. The company's physicians understood the mechanism by 1905 at the latest. The published internal correspondence confirms it. What the physicians were not authorized to do was disclose it to the workforce. The slow death was the manageable death. They came from Croatia, from Ireland, from the exhausted mining districts of Cornwall and Wales. They came from the copper ranges of the Upper Peninsula, following the work southward and westward as older deposits thinned. They arrived in Anaconda and Butte and Garfield with skills that were marketable precisely because those skills required a tolerance for conditions that most men would not willingly sustain. A converter operator's shift ran 12 hours. In summer, the aisle temperature at floor level exceeded 130 degrees Fahrenheit. Men drank water continuously and still lost dangerous volumes of fluid before the shift's midpoint. Burns from splatter were so routine, they were not reported. A man who reported a splatter burn risked being assigned to worse work. They lived in company boarding houses where the walls held the same mineral smell as the converter aisle, because the same air moved through both. They attended company physicians when ill. They were buried when they died prematurely, and they died prematurely at rates that the company's own actuarial tables recorded without comment, in parishes where the priest knew better than to ask the nature of the work. Their children grew up knowing the cough, not as illness, as inheritance. In 1917, the speculator mine disaster killed 163 men in a single night, the worst hard rock mining catastrophe in American history. It did not happen at the converters, but it happened in Butte, inside the same corporate geography, under the same ownership structure, and it broke something that had been under pressure for 2 decades. The strike that followed was not only about the speculator. It was about the air, about the company physicians, about the 12-hour shift and the $2.50 wage, and the boarding house and the cough that the men had no name for because the company had withheld the name. The Anaconda Copper Mining Company's response was methodical. It hired the Pinkerton National Detective Agency. It had strike leaders surveilled, dismissed, and in at least 2 documented cases, physically removed from the district. It obtained injunctions. It lobbied successfully against proposed state ventilation standards in 1918, arguing that the cost of converter hood installation would make Montana copper internationally uncompetitive. The ventilation standards were not passed. The converters continued to operate without modification. The grid continued to expand. By 1920, the United States had the most extensive electrical transmission network in the world. 40 million Americans had access to grid electricity. The copper wire carrying that current, strung across 150,000 miles of transmission infrastructure, had been refined, in significant proportion, through the converter systems of the Anaconda Company and its subsidiary operations. The epidemiological consequences were never formally aggregated. No federal agency compiled the respiratory mortality data from smelter communities into a single report. Montana's state health records from the period are fragmentary. What survives are the individual company medical ledgers, the pension denial letters, the parish death registers that list cause of death as pneumonia or cardiac failure in men aged 38, 41, 44. Men who had worked the converter aisle for 15 years and whose lungs, had they been examined, would have shown the unmistakable fibrotic signature of chronic sulfur dioxide exposure. The grid did not record this cost in any ledger that was meant to be read. Progress, in the industrial age, was denominated in kilowatts. The denominator beneath that fraction, the human one, was considered a rounding error. The Washoe stack still stands. It stands in a state park now, preserved as a historical monument, its 585 feet of brick rising above a valley floor that was declared a Superfund site in 1983, one of the largest environmental remediation zones in United States history. The soil around it contains arsenic, lead, and copper particulates at concentrations that exceed federal safety thresholds across an area of 300 square miles. The grid it helped build is still running. Expanded, modernized, restructured a dozen times across 100 years, but continuous, an unbroken electrical inheritance stretching from the Pearl Street station of 1882 to the infrastructure that carries power into 140 million American homes today. The men of the converter aisle left no monuments. Their contribution is not commemorated on the transmission towers. Their names were not recorded at the moment their lungs began to scar. They are present only in the silence inside certain parish records, in the actuarial anomalies of certain pension files, in the particular quality of absence that surrounds industrial history when it has been deliberately, systematically, and successfully managed. The wire carries current. It does not carry memory. That is left to us.